Consider the following situation. We have a box of mass m, which I haven't labeled, but let's say it has mass m. It's being pulled up and to the right by a pulling force of magnitude F. That force is oriented at an angle of theta above the horizontal. The interface between the surface and the box has coefficient of static friction mu sub s and a coefficient of kinetic friction mu sub k, and this is all happening on the Earth, and the box is initially at rest. So this is going to be a really comprehensive example. We can figure out all sorts of things. We're going to do this analytically. Here's some of the things we want to find out. We want to find the maximum magnitude that the force of static friction can have on the box in this configuration. We also want to find the actual static friction force magnitude in the event that this box is remaining stationary, that is if this F is not large enough. And then finally, we want to find the minimum magnitude of this pulling force F needed to overcome the static friction and put the box in motion if it is in fact indeed pulling at this angle theta above the horizontal. And in that situation, we want to find the acceleration of this box. Now, the first thing to note is that this is not a free body diagram. This is a schematic. We need to make a free body diagram in order to begin solving this problem, and that's what we'll do now. Obviously, we have the pulling force exerted up and to the right of magnitude F. Angle theta above the horizontal, which we'll put in there in a moment. We've got the gravitational force of magnitude mg exerted by the Earth on this box. We've also got an upward normal force exerted on the box by the surface that it's resting on. I'll call that little squiggly n. And we have a frictional force. Now, if it's static friction, in the case where it's not moving, we'd have static friction F sub s. In the dynamic case, when the box is moving, we'd have an F sub k. But otherwise, the static and dynamic free body diagrams would look the same. All right, so now we have our free body diagram. We can do a little bit more to it. Oh, and also we should choose a coordinate system. Let's take x to the right and y to be up. That's one thing we'll do. And we should also break this F into components. We might as well do that right now on our free body diagram to break it into components along our chosen axes. Now, this angle here is theta, so we have F cosine theta for the horizontal component and F sine theta for the vertical component. And so now we have our free body diagram, and we can begin to start solving this problem. To create some space, let's get rid of our schematic right here and replace it with our free body diagram, since it has all the necessary information. Okay, let's do part A. We know that the magnitude of the static frictional force must be less than or equal to the product of the static friction coefficient and the appropriate normal force. So this means that the maximum possible static frictional force will be equal to this product. So we can write that down. So we can see that what we need in order to get the maximum possible static friction force magnitude is the normal force magnitude. And we can get that from our free body diagram. Looking in the y direction, we see the normal force, we see mg, and we see a vertical component of the pulling force. Now, if this box is not going to be lifted off the surface, that means it's not going to be accelerating upward, and we assume that the surface is firm enough so that this thing doesn't accelerate sinking down into the surface. So that means there's no acceleration of this thing up or down, no acceleration in the y direction. So we can use that fact along with Newton's second law. So the y component of Newton's second law says that the sum of the y component forces acting on the box equals the mass times the y component of the acceleration of the box. Alright, so we can apply this, and we also know, of course, that this y component of the acceleration of the box is 0 for reasons we just discussed. So on the right hand side of this equation we have 0, and on the left hand side, well, we can write this all out. So here we have all the vertical forces with vertical components, or the vertical components of those forces. Normal force, totally vertical, F sine theta right here, mg here, and I chose up as my positive y direction, so this has to have a minus sign in front of it. And on the right hand side, m times 0 is 0. Alright, we can solve this for the normal force magnitude. And finally, we can plug this normal force magnitude in right here to get the maximum magnitude of the static friction force possible. Note that if this, F sine theta, were greater than mg, we'd have a negative normal force. That obviously can't happen. That relates to our prescription, or our situation that we're saying we're trying to figure this out in the situation where this thing hasn't been lifted off the surface. If F is big enough, and this exceeds mg, then there will be no normal force. The box will be lifted and accelerated up off the surface with some vertical component, and there will also be no static frictional force, or any frictional force of any kind, because there will be no contact. So you always have to keep these parameters, these constraints, in mind. Alright, so now we have actually found the maximum possible static frictional force. It has this expression, which depends on parameters of the problem: the static friction coefficient, the mass of the box, g, the acceleration due to gravity magnitude, and the magnitude of the pulling force and the angle. All things that we would imagine might be important in our actual problem here. Now, these results are useful. We might want them for further parts, so just in case, we're going to move them over here when we work on parts B and C. Okay, now that we've found the maximum possible static frictional force for this configuration, we can move on to finding the actual static frictional force in the event that the block remains stationary. So this, of course, this is the maximum value, but it may not be that value. Let's find the actual value, assuming stationary. So here we go. Looking at our free body diagram, we see in the static situation, the static frictional force is to the left. That's horizontally to the left. What's going to be relating to that is this component of the pulling force that's to the right. We see no other forces on this diagram that are going left or right. So now, if the block is going to be stationary and remain stationary, that means there's no horizontal component of the acceleration. In our coordinate system, that means no x component. So let's look at Newton's second law in component form in the x direction. The sum of the x component forces acting on the block must equal the product of the mass of the block and the x component of the acceleration of the block. So that's Newton's second law in component form in the x direction. Okay, so now we need to go to our free body diagram, identify those things that are in the x direction, and write them in. So we have F sub s to the left, so they'll have a negative sign in front of it, because that's going to be in the negative x direction. We have this to the right, and the acceleration of the block, well, if it's stationary and remaining stationary, that's 0. So let's plug that all that into our Newton's second law equation. We can solve this then for the static frictional force magnitude, and finally we get that the magnitude of the static frictional force that the surface exerts on the block is just equal to the strength of the pulling force F multiplied by the cosine of theta, theta being the angle of inclination that the force has relative to the horizontal. Now, we didn't really need to go through all this in gory detail. We could have done it conceptually, apply Newton's second law in the horizontal direction conceptually. If there's no horizontal acceleration, then the horizontal force components must balance. There being only two horizontal force components, they must have the same strength for there to be no acceleration, and that's what we see right here. Alright, so now we can take this result, put it over here on our results, and go on to part C. To find the minimum magnitude of the pulling force F needed to overcome static friction and put the block in motion, well, what that means, this has got to be big enough to overcome this when it's at its maximum value. So we need to put in F sub s max for F sub s on this free body diagram. Now, conceptually working with this, in order for this to break free of static friction, we need to have the F cosine theta greater than or equal to this. And actually it needs to be just a hair greater, all right? So we can write that in terms of our Newton's second law equation as follows. So the sum of the forces in the x direction acting on the box must equal the mass of the box times the acceleration in the x direction of the box. Those forces are this one, where we've got to use the maximum possible static friction since we're just trying to overcome it. And then we've got the F cosine theta here. So to find the minimum F necessary to overcome static friction, we can go all the way down to the static limiting case where we still have no acceleration, so that this is just balancing the maximum possible static friction. So in that case, the acceleration, a sub x, will still be 0, and that'll allow us to find this minimum F. So plugging in, we have F cosine theta minus F sub s max, because we've got the maximum possible static friction, equals 0, just on the threshold of slipping. Now we can plug in this for F sub s max and try and rearrange this and do the algebra and solve for the necessary F. First we rearrange this, and then we plug in for F sub s max this, distributing the mu sub s through, and now we can rearrange and solve for F. Here I've just brought this over to here. Now we can factor out the F. And finally we can solve for this necessary F. And there's our result. This is the value of the magnitude of the applied force F that would put us on the condition of the threshold of slipping. Any hair over this and the mass would break free and begin to slide and move from the static case to the dynamic or sliding case. So now that we have this minimum F needed to overcome static friction or put us in that threshold case, let's imagine now that the block is broken free and is sliding, so it's now in the kinetic case. We'll have an F sub k instead of an F sub s. Let's find the acceleration if it is sliding but has this force F magnitude operating from what we just calculated, that threshold force. So let's set it up and make this calculation. So again, we write Newton's second law in the horizontal direction, noting of course that the acceleration is not going to be 0. If this force, this value of F, was just enough to balance static friction, the maximum possible static friction, well, it's going to be greater than, well, F cosine theta will be greater than F sub k, because F sub k is less than F sub s. So let's figure this out. First we plug in the forces in the x direction, then we can solve for the x component of the acceleration. We note what F sub k is. Now of course this F here and here has this value, but let's take stock of what we have here before we go and complicate things further by plugging in F. Here I've got F cosine theta minus S sub k, that's this. I've distributed the mu sub k here and there, and distributed this minus sign through there to get a plus. Let's combine these terms with F, and then we can plug this value of F right in here. So now we see there's an mg here and an mg there. We can factor those out. The m's will cancel, just leaving a g on the outside, and that'll finally give us our result for a sub x. And so this is our result for the x component of the acceleration. Remember, there's no y component of the acceleration. So this is our result for the x component of the acceleration if this applied force F is such that would have been just on the threshold of slipping in the static case, and then when the thing starts sliding, we maintain that same value of f. Now, let's try to do some reality checking. Now, when you've got a complicated expression like this, it may be difficult to really do full reality checking, but let's do the best we can, and we can actually do quite a lot. First, let's notice that the units are correct. We've got a sub x equals g times a bunch of crap. Now look at all this stuff. Mu sub k, that has no units. Mu sub s, that has no units. Cosine theta, sine theta, cosine theta, sine theta, mu sub s, all that has no units. So the units of our result are just units of g. So at least our result has the right units. Now let's do some reality checking with regard to, like, the size. So first of all, normally F sub k is less than the maximum possible static friction F sub s. That's because mu sub k is always less than mu sub s. So now, what if we had some weird situation where the static friction for the static connection friction coefficient mu sub k were the same as mu sub s? Well, if that were the case, then if this F were such that F cosine theta balanced F sub s max, then if we had the same value for these coefficients of friction, then F cosine theta would also just balance F sub k, and the acceleration should be 0. So let's see if we actually get 0 acceleration if we replaced mu sub s with mu sub k or vice versa. So let's look. So we've got this term here, cosine theta plus mu sub k sine theta, and here on the denominator we got cosine theta plus mu sub s sine theta. If mu sub k and mu sub s had the same value, this parentheses term and this parentheses term would be the same, so they'd cancel. And we'd have g times the quantity mu sub s minus mu sub k. And if those, again, mu sub s and mu sub k were equal, we'd have g times 0, giving us 0 a sub x. So at least our result checks out in that way. So we can check the limiting case, and we can check the units, and then we can have some degree of confidence that our answer is indeed correct.